Hello, my name is Dominic Boats, and this is the final exam video submission. So, for this video submission, I will be making a correct Lewis structure for C5H8O. So I'll write that up here. C5H8O. Okay, so what we're first going to do is we're going to look at the elements. One thing that we know about carbon is that it likes to bond and make 4 bonds. And then looking at hydrogen, we know that hydrogen only makes 1 bond. And then next we look at oxygen, and oxygen likes to form 2 bonds. So what I'm going to do is, since I got 5 carbons, I'm going to write them in this shape. 2, 3, 4, 5. And I'll connect all those up, just like so. And then I'll draw my hydrogens. And again, hydrogen only likes to make 1 bond. So I'll put 2 hydrogens on each carbon. I'm just drawing my bond lines first. Put an H, 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 put an H. Now we have 1 carbon left up top, and that will be where our oxygen bonds. Now we can't just have 1 bond here because oxygen likes to form 2 bonds. So in this case, it will be a double bond. And then now oxygen isn't fulfilling the octet rule because it's only got 1, 2, 3, 4 electrons. So what you do is you add 2 lone pairs on top of oxygen. And that is the complete Lewis structure of C5H8O. Now, and to check, what you do is you can actually go on a P table and you can add up all of the valence electrons. In this case, this has 34 valence electrons. And then what you can do is you can look at your Lewis dot structure and you can add up everything to make sure you have enough. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, which is exactly what we wanted. So that means that this is correct. So next, what we're going to do is we are going to look at the molecular geometry. So when doing that, and we're going to look at the molecular geometry of each individual bond. So we're first going to look at one of the C3H2. So in that case, we'll have C as the central bond, or the central atom, and then we'll draw the other ones. So then we have 2 H's. Put an H here, put an H here, and then we know that we have 2 other C's. So in this case, when looking at it, we know we can look at, if we look at the central atom, C does not have any lone pairs, so there's 0 lone pairs, but there are 1, 2, 3, 4 bond angles. So that means that there's 4 electron groups and there's 4 bond angles. So when we look at our chart, we find out that the molecular geometry is tetrahedral. It's not too good, but tetrahedral. And then if we look at the electron geometry, so we look at the chart, and again, looking for something that has 0 lone pairs and 4 bond groups, then you also get tetrahedral. Now, looking at the charts, we'll look for the bond angle. So the bond angle, looking at the charts, we find out is 109.5 degrees. So that is what the molecular geometry, electron geometry, and the bond angle for this bond. Now we look at our next bond, and the only other bond in this case is the C3O. So in this case, we have C as the central atom again, And then we have these, but again, the O is a double bond. You have its 2 lone pairs, and then you got the 2 carbons. So now looking at this one, it's different. So we find out that this actually has, so we find out it's got 2 lone pairs, and it has 3 bond groups. So when determining the molecular geometry, you'll find something to match up that has 2 lone pairs, and then 3 bond groups, but in total it's got 5 electron groups. So when we do that, we find out that the molecular geometry is T-shaped. Nope, looks like I'm going into print. And the electron geometry is trigonal pyramidal. Big word. Trigonal pyramidal. And when looking at the chart, we find out that the degree for the angle is 90 degrees. So that is the classifications for molecular geometry and electron geometry and the angles for the different bonds of the Lewis structure. So now what we're going to do is we are going to look at the polarity. So in general, we know that for when finding polarity, what you want to do is find the change in electronegativity. So when looking at the change of electronegativity for a carbon and hydrogen bond, so C minus H, well, that is, we look at our P table, we find out that carbon has a 2.55 electronegativity, and then you subtract hydrogen, and hydrogen has a 2.20 electronegativity. And when we do that, we find out that the change in electronegativity is 0.35. So, what we do, and now to determine if it is polar or nonpolar, we look, and you just kind of have to know this. So if something is polar, or for something to be polar, it has to be greater. So polar equals, it has to be greater or equal to 0.5. So in this case, the carbon and hydrogen bond, the change in electronegativity is 0.35. So that is lower than the 0.5. So we know that this is a nonpolar covalent bond. So now looking at the bond between, let me get this right, the bond between oxygen and carbon. So the bond between oxygen and carbon. Now when looking at P table, we find out that the electronegativity for oxygen is 3.44, and then you'd subtract the electronegativity of carbon, which is 2.55. When doing so, you get 0.89. And again, now looking up here, is 0.89 bigger than 0.5? Heck yeah, it is. So that makes the bond between oxygen and carbon a polar covalent bond. Now, looking at the molecule as a whole, what we're going to do is we're actually going to draw the moment arrows. So, in this case, we look at hydrogen and carbon. So, hydrogen has a smaller electronegativity than carbon. So, it's going to have arrows pointing towards carbon. And that would be the same for all these. So, when we do that, we're just, the hydrogens get canceled out and we're just left with the carbons. Now what we're going to do is the carbons bond with each other. Now in this case, both carbons had the same electronegativity, so then that would just cancel these out because they would be 0 because they have an electronegativity of 0. So I would cancel out these two and these two. And then we're just left with the bond between the carbon and oxygen. So in this case, so just how it was up here, so oxygen and carbon bond, which equals 3.44 because that is the electronegativity of oxygen minus 2.55 because that is the electronegativity of carbon equals 0.89. And again, 0.89 is bigger than 0.5. So the molecule as a whole is a polar covalent bond. So that is how you find the polarity of it. And then lastly, for the question and going for the bonus now, we are going to draw a structural isomer of the C5H8O. So an isomer is a different structure, but it still has a different structure and like different bonding, but it still has the same formula. So when doing that, what I'm going to do is I'm going to first draw my C's. In that case, we know that we have 5 C's. So I'll put, making sure we can see it. Okay, I'll put 1 C here, and I'm going to put 1 C there. I'm going to put 1 C here, 1 C here, 1 C here, and lastly 1, 2, 3, 4, our last C. And then what we're going to do is just simply draw up the bonds. Now this isn't going to be like set in stone. And now what we're missing is our hydrogens. So we're just going to attach our hydrogens like usual. So hydrogens are still single bonds. So I'll put a hydrogen right up here, hydrogen right up here, hydrogen right up here, hydrogen up here, and I'm going to attach a hydrogen right there. Now, what we're missing, and you probably can tell, is our oxygen and our last hydrogen. So in this case, our oxygen still likes to form a double bond, not a double bond, but 2 bonds. But in this case, since we still need to attach our hydrogen, we're going to have the 2 bonds being that way and attach our last hydrogen this. Now, going back and correcting some things. So oxygen, that is not fulfilling the octet rule yet because it's only got 1, 2, 3, 4. It's only got 4 electrons. So what we're going to do is add 2 lone pairs. Just like that. Hydrogen's working good here because it's got 1 bond. Carbon, oof, that's looking a little, or wait. Oh, I forgot some hydrogens. So, wait, 1, 2, 3, 4, 5. I got that right. Oh, that's why. Sorry, I misplaced the hydrogen. So I'm actually supposed to have 2 hydrogens right here. Sorry, excuse my mistake. And the reason why I had my hydrogen misplaced is because in this case, this carbon would not have enough to fill the octet rule. Yeah, so now it does, and it's got its 4 bonds, so it's all happy. So now we're left with this carbon. Now if we look at this carbon, it doesn't have 4 bonds either. It's not happy. So what we're going to do is make this one a double bond. And now this has 1, 2, 3, 4. 4 exact bonds. So it is a cool dude now. Now we go over here, and this has the same thing that went on over there. It used to have 3 bonds, but now because of the double bond, it has 4. So this carbon is happy. So looking at this carbon now, it has 1, 2, 3, 4 bonds. So that is all happy. And then, oh, looking at this one, it's got 1, 2, 3, only 3 bonds. So we're gonna make this one. Oh, I messed up again. That is not supposed to be there either. Sorry about that. Yeah. Okay. So this, and the reason why is because that would have messed up this bond right here. So when I take off that, then that leaves both of these with 3. And just kind of how we did over here, we'll make this one a double bond, and that fulfills this one. 1, 2, 3, 4. That's got 4 bonds, so that is happy. And 1, 2, 3, 4, so that one's happy. So that is, and looking over fully, and again, we can check to make sure that this has the same formula as this one. So we'll just count up. So counting up the carbons, we have 1, 2, 3, 4, 5 carbons. So we have, if it will write, here, I'll put it up here. We have C, oh my gosh. Okay, we have C5. That won't show up, but whatever. You can just trust me. And then we have 1, 2, 3. Wait, start from the corner. 1, 2, 3, 4, 5, 6, 7. Exactly 8 hydrogens. Still can't see it too well. And we have our 1 oxygen. I wish it would write, but being my luck, it is not wanting to work. Nope, I get a little bit. Okay, and that is an isomer structure of C5H8O. So yeah, and that is it. I hope I did good, and yeah, thank you.